Hello, welcome to the another little extra lecture for the Math 170 class this fall. And we were talking in class about backward error analysis. So the idea, again, for backward error analysis is we want to change an approximate calculation with exact data to an exact calculation with approximate data. And the reason for this will become clear a little bit later, but first let's talk about how to do this. So let's just do a quick example of how this could work. Let's say our exact calculation that we're trying to do is x plus y plus z. And let's say that we're doing the x plus y first, just to be really precise. So the computer, when the computer does this calculation, it's going to do actually c hat, which is floating point of floating of x plus y plus z. Right, this is the actual calculation it's going to do. It does x plus y, takes that as a floating point, then adds z and takes that as a floating point. So if we do it this way, this is x plus y, 1 plus epsilon, plus z, 1 plus epsilon 2. Let's call this epsilon 1. So you have a relative error from adding x and y, and you have a relative error from adding z to that. So you have two different epsilons there. But we could rearrange this. We could rearrange this as x, 1 plus epsilon 1, 1 plus epsilon 2, plus y, 1 plus epsilon 1, 1 plus epsilon 2, plus z, 1 plus epsilon 2. And that's fine. I mean, that's just some algebra. And then we could relabel this as x hat, this as y hat, and this as z hat. And so, instead of an approximate calculation with exact data, which is what c hat represents, now we can think of it as an exact calculation with approximate data. So here the x hat, the y hat, and the z hat are the approximate data, and we're doing an exact calculation. We get the exact same answer as if we did the approximate calculation with exact data. Now, of course, we don't know what the errors are unless we have numbers, so this seems like kind of just rearranging things, but it turns out to be a powerful, useful thing, so we're going to keep doing it. And if we can do this, we call a calculation backwards stable. So let me write that down exactly. So here's the definition. A calculation is backwards stable if an approximate calculation with exact data gives the same result as an exact calculation with very close approximate data. So in other words, if we have a calculation, we can always think of it as an exact calculation with approximate data. But in addition, we want the approximate data to be very close to the original data that we plugged in, just for it to make sense, really. And so, this very close is important because we need that in order to guarantee that our solutions are accurate using this method. So, as an example, if we're solving AX equals B on a computer, the exact solution is X equals A inverse B. That's just what you would calculate, say, by hand, if you could do it, just with infinite precision. Now, if we have an approximate solution, AX hat is equal to, if we have an approximate solution, X hat, that happens to equal, say, the float of A inverse B. So, we're just thinking of X hat being what you get out of the computer, right? We want this to be equivalent to saying we have approximate data, A plus delta A, B plus delta B, and X hat solves A plus delta A X hat equals B plus delta B exactly. And of course we want delta A and delta B small, relative to the size of B and A originally. So if we could do this, if we could say that our approximate solution that we got via, say, the Cholesky decomposition or the LU decomposition, if we could say that we got that approximate solution and it was the exact solution to a perturbed system, so where A and B and or B are slightly different, and these delta A and delta B are stable, are small, then the algorithm that we used was backward stable. So whenever we talk about backward stable, we're talking about a calculation or an algorithm. Calculations are algorithms, right? And so if this is true, it's backward stable. Now what do we mean by small? Usually small is supposed to mean that delta B over B, or a similar thing for A, is a, quote, modest multiple of the unit round-off. Like most of these accuracy things, small and modest and other things, there's a bit of wiggle room here because in different situations you might care about more or less accuracy. But a modest multiple of the unit round-off, if you had 10 times the unit round-off, that'd be great. Generally speaking, modest means something like n, the size of the matrix, n times the unit round-off. Something like that would be considered reasonable. All right, so now I want to ask you what would have been a question I would ask in class, a clicker question. So I'm going to write it up on the board, and then pause the video and see if you can answer it. Think about it for a minute before we're restarting it. So suppose we knew that Gaussian elimination was backward stable. We don't know that yet, but let's say we knew that. Then our answers to AX equals B are accurate. True or false? So pause the video for a second, think about that. If it's backward stable, then our answers are accurate. Is that true or false? All right, now that you have had a minute to think about this, the answer is false. So if we have an exact, if x hat, which is our approximate solution that we got from Gaussian elimination, if Gaussian elimination is backward stable, then x hat is a solution to an approximate problem. Say, for instance, a plus delta a, x hat equals b plus delta b. But to be accurate, you need kappa of a to be small also. And so the basic principle is that if you're backward stable and well conditioned, then you have an accurate solution. But you need both. If both of those are not true, then you don't know whether you have an accurate solution. You need both. All right, and that's it for this extra little lecture. Thank you.